All right, so next, in the context of Chapter 11, Ideal Solutions, we want to talk about phase equilibria involving non-condensable components. All right, and so first, what exactly do we mean by non-condensable components? So as we walk through this material, as we work through this material, the picture I'm going to have in my head is, say, of water and air. Why? Because water and air is typically something that we all can think about and readily appreciate, and is important for humidification processes. Okay, so if I think about a mixture of water, right, we'll let water be, say, component 1, and air. Okay, and so in the interest of our discussion, I'm just going to think of air as being a single component, right? But in fact, if my memory is correct, air is about 78% nitrogen, 21% oxygen, and then the balance is other non-condensables, xenon, argon, and what have you. Okay, so for the purpose of our discussion, I'm just going to think about air as being a single non-condensable component. All right, but again, in theory, air is essentially composed of nitrogen and oxygen. And what do we mean by non-condensable? So if I go to the appendix, the back of the book, okay, so if I'm looking at these two columns, critical temperature and pressure, okay, I go to water, critical temperature of water, 647 Kelvin, critical pressure is 220.64. So if I'm at atmospheric temperature and pressure, so say 298 Kelvin in 1 bar, I'm well below the critical point of water. Okay, but on the next page, we have nitrogen and oxygen. So if we look at oxygen, critical temperature of oxygen is essentially 155 Kelvin, and critical pressure is 50 bars. Okay, so if I'm at atmospheric conditions, 298 Kelvin and 1 bar, okay, atmospheric temperature is beyond the critical temperature of oxygen. Right, so the critical pressure is greater than ambient pressure, but ambient temperature is well beyond the critical temperature of oxygen. Okay, so that would essentially suggest to me that I'm going to have a superheated vapor, right, when I look at oxygen, and that I would need super high pressures, say, to be able to condense that component. Super high pressures, or if you actually want to think about cryogenic separations, what companies like Praxair do, you'd end up looking at really low temperatures. Okay, if I look at nitrogen, it's the same story. Okay, here's my critical temperature, here's my critical pressure. Atmospheric temperature is well beyond, so ambient temperature, 298 Kelvin, is well beyond the critical temperature of nitrogen. So I'm definitely going to have a superheated vapor, and it would require extreme pressures at that temperature in order to condense it. All right, so by non-condensable component, what I'm thinking of is, in terms of the conditions of the problem of interest. So here, if I'm thinking about water and air at 298 K in 1 bar, that under these conditions, I would really have to crank up the pressure in order to condense, air, right, to get air in the liquid phase. So I just refer to it as non-condensable, right? It's not going to be, it's not in its pure component state. You wouldn't find it as a liquid. Okay, cool. All right, so how we begin is, one, I'm going to write down Rayleigh law. So I'm looking at modeling water at essentially saturation with air. Okay, so I'm going to start by just writing down Rayleigh's law. Okay, so Y1P is equal to X1 P1 sat. Okay, and I just start by writing down Rayleigh's law. Okay, but in terms of thinking about what Rayleigh's law means and assumes, right, Rayleigh's law is actually a really, really good assumption. Right, so if I'm thinking about water and air, so I'm at, say, 298 K in 1 bar, so I'm at low pressures. Okay, assuming my vapor phase is an ideal gas is going to be a good approximation. Okay, looking over towards the liquid phase. Okay, well, so if I have a non-condensable component, so if I'm looking at air and water, okay, I know that the composition of water or air in water is going to be really small. Okay, we'll just say that it's going to be approximately equal to 0, so that X1 is going to be approximately equal to 1. Okay, we're going to be talking about really low compositions of air. Okay, we'll look at this in later chapters when we talk about Henry's law, but in general, the composition is going to be really small. Okay, and I know that all solutions approach, ideal solution behavior in the pure component limit. So if I expect x1 to be close to 1, then assuming I have an ideal solution is a really good approximation. And then again, if I'm at low pressures, vapor phase is an ideal gas, and then Poynting correction is negligible, are both going to be good approximations. Okay, cool. But if I further build upon this idea that the composition of component 1 is going to be close to 1, okay, then I can rewrite this then as just y1p is equal to p1 sat. All right, because x1 is approximately just equal to 1. Cool. I'm going to put a superscript on my y1 of sat to remind myself this is of saturation. And if I rearrange and solve for y1, I get y1 sat is equal to p1 sat over p. Okay. And so what this would correspond to is if I think about water and air, okay, this would correspond to the composition of water in my vapor phase. Okay, so this would be the composition of water in my water-air mixture. Okay, at which point water would begin to condense out of solution, or condense out of that vapor phase. Right. So if I'm thinking about the atmosphere, okay, this would be when it starts to rain. Right. This would be when I start to get water condensing out of my vapor phase. Okay, cool. And so the next thing we're going to introduce is we're going to introduce another term called the relative humidity. Okay, and so the whole idea behind relative humidity, okay, so if I look at this equation, which just stems from Rayleigh's law, okay, this would correspond to the composition of, say, water in my vapor phase, at which point it would begin to condense out of solution. Okay, so P1 sat is going to be a function of T. Okay, P is P. Okay, and so the whole idea behind relative humidity is just how close am I to saturation. Okay, so if I had a vapor composition of water that was some value, and it was less than y1 sat, all right, well then my vapor phase isn't at saturation. Water's not going to begin to condense out of that vapor phase. Okay, and so the whole idea behind relative humidity is, well, how close am I? Okay, and so relative humidity is just defined as being y. Okay, so this would be the composition of water in that vapor phase relative to y1 sat. Okay, y1 sat would correspond to the saturation composition of water at T and P. Remember, P1 sat is a function of T, P is P. So at a given temperature and pressure, all right, I can measure y1, say my vapor phase. Then I could calculate y1 sat via this expression. So the relative humidity is going to tell us how close y1 is to y1 sat. Okay, if relative humidity is 1, that means y1 is equal to y1 sat. That means I'm at saturation. Water is going to begin to condense out of my vapor phase. Okay, so how this is typically written, and why I put that superscript of sat on there, is I can plug in for y1 sat, p1 sat over p. Okay, so this becomes y1 divided by p1 sat over p, or finally y1p over P1 sat. Okay, and if you really wanted to, you could write this as partial pressure, just P1. Okay, so my relative humidity is defined as Y1P over P1 sat. Okay, the picture to keep in mind when you think about relative humidity is you're looking at the composition of component 1 in my vapor phase and looking to see how close it is to the composition at saturation. Okay, cool. Okay, so that is relative humidity. All right, that's phase equilibrium involving a non-condensable component. Okay, now we'll look at some example problems in which we'll see applications, but let's just kind of talk about this a little bit. Okay, first example that comes up in the notes is a hot summer day. I go outside with, say, a cold cup of water, and I immediately see that water begins to condense on my glass. Okay, what is happening? Okay, well, if I think about what's going on in a summer day, is I watch the news in the morning, so or I look at my app on my phone. It's 298 Kelvin outside. I know the pressure is 1 bar, atmospheric pressure, and oftentimes I'll even tell you what the relative humidity is. Okay, but if you just want to think in Oxford, okay, so Oxford, we're at some steady state in which the composition of water and air everywhere in Oxford is some Y1. Okay, and I know the pressure is going to be same throughout Oxford. It's going to be some pressure P, 1 bar. Okay, cool. Well, so what happens is if my relative humidity is less than 1, okay, then water is not condensing out of air. It's not raining. Okay, that actually tells me the air can hold more water. Okay, but what happens is, so I'm going to have a relative humidity less than 1. Okay, throughout Oxford. But then what happens is when I put my cold cup outside. Okay, now remember P1 sat. This is my pure component vapor pressure. It's only a function of T. So as temperature increases, P1 sat increases. As temperature decreases, P1 sat decreases. Okay, so what happened is when I put my cold cup outside, okay, so essentially this has become a heat transfer type of problem, but the idea would be I put my cup outside. In the immediate vicinity of that cup, okay, if I just think about the that cup is going to be at a lower temperature, right? So if it's ice water, it's going to be at, say, 0 degrees C. It's going to be close to the triple point of water. So I put my cold cup outside. Now, in the vicinity of that cup, my temperature is 0 degrees C. Okay, so the temperature is lower than the temperature outside. So P1 sat is going to decrease. Okay, what happens as P1 sat decreases is my relative humidity increases. Okay, when my relative humidity hits 1, water begins condensing out of my vapor phase. Okay, and again, we'll look at an example with humidification where you can compute how much water and things of that nature would come out of the vapor phase. But the idea with your cup of iced tea or a cup of cold water is you have a cold cup of water. It's going to decrease the vapor pressure in the vicinity of that cup, which leads to reaching relative humidity of 1 in that local area, and then water begins condensing out of solution. Right? Cool. Other cool applications, as you think about non-condensable components, is sweat. Right? So sweat's one I bring up a lot because I want to say there was actually an old Ben Franklin patent about putting wet towels or wet sweaters on or something of that nature in summer to cool off. Okay, and the idea is if I were to have a cup of water. Okay, so I live in the desert, so I live in, say, Albuquerque, New Mexico. If I were to have a cup of water and I just left that out on my counter, I know that over time, eventually the water from my cup is going to evaporate. Right, the water level is going to decrease. Even, I'm from Buffalo, New York, so near Lake Erie, and so I still remember as a kid, we'd fill up the pool in the summer, and throughout the summer, you would continuously need to add water, right? You would lose water throughout the summer, all right? What's going on, all right? And so in the same token, my pool as a kid was technically boiling, as is, Lake Erie. So if you think about it, so if the relative humidity outside is less than 1, okay, so when I have a relative humidity of 1, I'm at equilibrium, all right? Nature wants to be at equilibrium, right? Be at a state of equilibrium. So if I have air in contact with my pool, okay, and the vapor composition of water in my air is less than Y1 sat, or I have a relative humidity less than 1, then there's going to be a driving force. Okay, this is going to become a mass transfer problem. There's going to be a driving force for water to leave the liquid phase and go to the vapor phase until equilibrium is established. All right, so there's going to be a desire for water to leave the liquid phase and go to the vapor phase until it establishes a state of equilibrium with a relative humidity of 1. Okay, now remember when I get Y1 sat, that's kind of like my dew point, right? It's this theoretical limit where water would begin to condense out. Okay, and so water is going to continuously leave my pool until that equilibrium state is established. which actually brings me to another thing that often comes up. So if I look at this equation, y1 p is equal to p1 sat. Okay, where I say, my pool is boiling, Lake Erie's boiling. Oftentimes you have in your head that water boils at 298 Kelvin in 1 bar. Okay, well, what that pertains to is a system of pure water. Right, that would correspond to a system of pure water. Right, remember we're talking about pure component phase coexistence. Here we have, air involved, right? So it's not pure water, right? Now we have air, okay? And so what the effect of air is essentially reduce my pressure, okay? So it's going to reduce the partial pressure of water, okay? And so when, my pool is losing water when water is evaporating, technically you could say it's boiling, right? It's just, when my pool is open to the atmosphere, right, I no longer have, a system of water at 1 bar, at which point it would boil at 100 degrees C. No, right, I have water at this much smaller partial pressure because that water is diluted by air. All right, cool. Which brings up kind of then the idea of sweat, right? So the idea of sweat, why I sweat in the summer, why we sweat. It must be some sort of genetic adaptation. Is the whole idea is you get water on your body, okay? Your body releases water, and water sitting on your skin, and then it evaporates, right? So essentially, relative humidity is less than 1. There's a driving force for that liquid water to go to the vapor phase, and it boils, it vaporizes. Okay, and that's going to remove heat equal to the enthalpy of vaporization from you, right? Remember that delta H due to phase transition is going to be greater than, say, some delta H within a single phase over some limited temperature range. Okay, so I sweat because that's water vaporizing. That's going to remove heat from my body. It's going to cool me off. Cool. All right, so there's some cool examples. And really, it's kind of endless. If I think about being from Buffalo again and lake effect snow, right, it still has to deal with this non-condensable component business. Okay, in the winter, I have a cold air mass in Canada. Right? It's this cold, dry air mass, right, that now comes over Lake Erie. Okay, so in the winter, the Great Lakes serve as a heat source, right? It's a large body of water. It takes a long time for them to cool down. Okay, and so what happens is when this cold air mass comes over warm Lake Erie, okay, so it temporarily warms up, okay, so that means that it can hold more water, right? So it's going to warm up this dry air mass coming over the lake so that it can retain more water. So water gets sucked up from Lake Erie to this air mass. After it comes over the lake, it moves back over this cool land, right? It comes back over land, no longer water source, and the temperature drops down, okay? And as the temperature drops, all right, it's the same thing as my cool cup of water. P1 sat goes down, relative humidity goes up. All that water that it just sucked up over the warm lake comes out on me, okay? It's endless. So I went to St. Louis once. St. Louis is known for having really, really high relative humidities in the summer. Why? Because it's situated, it gets warm there for one, and it's situated right next to the Mississippi River. Okay, and so large amounts of water vapor are sucked up into the air. Okay, and then what's going to happen is the closer your relative humidity is for one, right? This becomes a mass transfer problem. So I sweat with the idea that relative humidity is less than 1, it's going to vaporize. Okay, and so thermo tells me that, but mass transfer is going to tell us how quickly it vaporizes. So if my relative humidity is really close to 1, the driving force for mass transfer to go from water on my skin to that vapor phase is going to be a lot smaller, and so you end up being awfully sweaty in a place like that because your sweat's just not vaporizing all that quickly as compared to a place like Albuquerque in the middle of the desert. Okay, And so if you're still watching after me talking about all these hokey examples, that's great. I'm trying to think if I can think of any other corny ones to tell you, but I think that's about it, and we'll wrap it up for you. And again, we'll look at a couple of examples where we can see these things in practice. So when we say, thinking about my dehumidifier in my basement, so there's going to be some cooling coils that water is going to come in contact with. The cooling coils will decrease the local temperature, decrease P1 sat, water condenses out. Thinking about, how much water is actually being removed, right? And so we'll look at that in a couple of the examples. Okay. Let's look at two more examples as I talk about my dehumidifier. Again, this is if you had me in class. First being, thinking about being here in Oxford. In the winter, I need to actually run a humidifier in my house, right? So what's going on in the winter, right? Otherwise, in the winter, my skin often gets very dried, and it becomes problematic, right? The key is to think about, relative humidity. Think about that cold cup of water case, okay? So outside, right? So outside in Oxford, okay? Relative humidity is going to be less than 1. There's going to be some mole fraction of water in air, across the entire town. And then, our pressure is going to be 1 bar, right? The entire town's at the same pressure, okay? Now, technically this could become a mass transfer problem, but thermo is the main act at play, okay? So there's going to be some relative humidity less than 1 across the city, unless, of course, it's snowing, okay? But I have some relative humidity less than 1, some fixed mole fraction of water in the air, and some P. Okay. Then what happens is, if that air, say, were to enter my house. Okay. So now in my house, I'm burning natural gas, so I have a heater. Okay, that increases the temperature. Right. It's cold outside. I need it to be warmer inside. Okay. Or maybe you're, have a fireplace. Okay. Whatever the case, say air from outside comes in my house. And now the house temperature in my house is much higher, okay? And so what happens is this air at this same Y1P partial pressure of water enters my house. Temperature is much higher, so as temperature increases, P1 sat increases, so the relative humidity decreases, okay? And so now this becomes, mass transfer. And what I mean by that is, I have water in my skin. Okay, and so even in a hot, humid day, water is being sucked out of my skin. As the air attempts to, reach a state of equilibrium with us. Okay, but the lower that relative humidity is, the greater the driving force for mass transfer. Right, the greater the relative humidity, or closer it is to 1, the lower that driving force. So what happens in the winter is when the air enters my house at a high temperature, relative humidity really drops down. Okay, so relative humidity drops down or decreases drastically. So there becomes a large driving force for mass transfer for water to leave my skin and go to the vapor phase, right? Which causes me to get dried out. Okay, so the purpose of a humidifier then is to add air add water to air to increase my relative humidity, to decrease that driving force to get to be dried out. And actually, a humidifier is a cool thing, thinking about water boiling, because that's what's happening, right? But now I have my tank of water at the temperature of my house, and then essentially what it does is it tries to increase mass transfer, increase the rate of vaporization of water. And so typically you have a fan that's going to blow droplets of water into the air. So it's going to disperse them, decrease the surface area of those droplets, which readily makes them more readily able to transfer to vapor phase, right, where they're wanted, because I have my relative humidity less than 1. Okay, and so me getting dried out in the winter is just like the case of like affects snow. In the summer, I need to flip things. I have a dehumidifier in my basement, right? In my basement, so my basement's underground, and so my basement's gonna be cooler than it is outside. Okay, and so what'll happen is, air comes inside, it cools down, so it gets closer to having a relative humidity of 1, and I don't want water condensing on the walls of my basement. That'll lead to mold and things like that. So dehumidifier helps remove water from the air and decrease that relative humidity, so I don't have any cases of water condensing on the walls of my basement. Okay, but it's cool, right? And it's all based on kind of these simple relationships. And so it's important that you kind of keep these in mind, right? Think about the thermo. And so if you ever encounter one of these scenarios, you have an idea of what's going on, and then maybe how you might influence things or things of that nature. Okay.